Hello, I'm Graham Lewis, and in this video we're going to discuss inference about regression. We're going to look at the slope of a regression line and make inference about the population slope from our sample. So let's look at an example here. So here we have a sample of 250 men, and we've measured their waist circumference and their percentage body fat. And we ran regression, and we got that the percentage body fat from our regression line from our sample was equal to minus 42.7 plus 1.7 times their waist. So, for example, in this sample, we can say that a 1 inch increase in their waist will give a 1.7% increase in their percentage body fat. Now, let's have a think what's actually happening here. We've got y hat, our fitted y values, as before is b0 plus b1x, where b0 is our y-intercept and b1 is the slope of the regression line. Now, what's actually happening here is the regression line is actually attempting to fit the line of best fit through the means of all of the different normal distributions for a given x. Let's just explain that a bit more clearly. I have a 32-inch waist at the moment. So imagine my 32-inch waist, and the mean of all people with 32-inch waist body fat is here. So that's the mean of all people. But we'd expect everyone with a 32-inch waist to actually have variations in their body fat. They wouldn't all be exactly the mean. And that's actually normally distributed there. So you can see that some people with a 32-inch waist might have a much lower percentage body fat, and some people who have a higher percentage body fat than the mean. What the regression line does is fits the line, attempts to fit it through the means of those and that dotted line there. But the problem is it will fail, and it will of course have variation in that, so there will be errors. So now let's think about not our regression line we found here, but actually what the actual regression line would be if we had the whole population, because we want to take our sample regression line and make inference about the population regression line. So here's probably a new idea for you. For the population regression line, we actually have that the actual regression line, which I'll call mu y, is beta 0. We use, again, for population, we use the Greek letters instead of b0, and beta 1x, where beta 0 is the true population y-intercept of the line, and beta 1 is the true population slope of the line. But we know we're going to have errors, so we'll call those epsilon. So that's actually the correct model there for the population regression line. Now, we have taken a sample of 250 men, and from our 250 men, we've got an estimate of beta 0, which we're calling b0. That's our actual regression line y-intercept. And we've got an estimate for beta 1, b1. And b1 is estimating beta 1. So it's really important to think of that b0 is an estimate of beta 0 and b1 is an estimate of beta 1. And of course we want to make inference from our sample. What does our regression line actually tell us about the population regression line for the whole population of men, not just our sample? Now, the way that b0 and b1 are estimated is in a statistical method called the linear estimator. So interestingly, linear regression is not called linear regression because it is a straight line linear. It's actually called linear regression because the way that beta 0 is estimated is a linear estimate, a linear estimator. So that's a little bit more advanced, and some of you at university may see that in the future. Now, those that go on to study some more statistics at university will find that linear regression moves into multiple regression. And multiple regression is when we have more than one explanatory variable. So we've only done b0 plus b1x, but what if we also had another variable x squared and another one root x? So basically, multiple regression is when we're allowing many explanatory variables, or if it's a science experiment, independent variables. Multiple regression, which is not in AP, you use the r squared adjusted in the computer output, not the r squared. So r squared is purely for regression when there's only one explanatory variable, In our case, in AP, that's the case. But when you go on to do multiple regression, you use R² adjusted because it's a better estimate for the fit. Now, here, this is still linear regression, believe it or not, even though it's got an x² and a root x term in. And again, it's called linear regression because B0, B1, B2, B3 are linear estimators of beta 0, beta 1, etc. So that's the reason it's called linear regression. So now let's go ahead and do an example on inference about the slope. So we've got our sample regression line and we've got a slope. It was 1.7%. So we know that we from our sample, a 1 inch increase in waste gives a slope of 1.7%. So what we're going to do is set up the null hypothesis that the population parameter, the slope of the population regression is 0, and the alternate hypothesis H1 or HA is the slope of the population regression is not 0. Now, it doesn't actually make sense much to do inference on the y-intercept often, because often the y-intercept is extrapolation and it's not interpolation. So unless the y-intercept is interpolation, you don't really need to worry about the y-intercept, but the y-intercept one would be set up the same way. Let's assume that the y-intercept is 0 and the alternate, the y-intercept not 0, and we can discuss that when we see the computer output later. Let's discuss the assumptions and conditions for this hypothesis test. Now, it's really important when you do the assumptions and conditions that you do them in order. So firstly, you look at your scatter plot. Don't look too hard, have a quick glance. One of my old professors said, if you look hard enough, you'll find a pattern that's not there. So have a quick glance, is it straight enough? Look for those parallel train tracks, is it straight enough? And you may need to transform the data to make it straight enough, which I'll discuss in another video. Independence. The errors, epsilon, must be mutually independent. This is really hard to check, but randomization does protect us. You need to have equal variance. Something that happens very common is this fanning effect here. So this is called heteroscedasticity, and that fanning effect is very common and it causes a problem, and we need to fix that. And the nice thing is we can fix that with transforming the axes often. So look for heteroscedasticity as well as curves and things like that. And you might see that in the original plot, or you might see it in the residual plot. Okay, let's have a look at the other conditions. Now we're assuming that for a given x, the y's are normally distributed. So in our example, we said for people with, say, a 32-inch waist, that everyone with a 32-inch waist, their body fats are normally distributed. Because we're using a t-test and we've got two unknowns, mu and sigma, we're going to have n-2 degrees of freedom. The residuals must satisfy the nearly normal condition. So we'll need to draw box plots and look at outliers. We'll have to draw histograms, normal probability plots, and to check that the residuals satisfy a nearly normal condition. And we need to do all of that in order. Now let's do the mechanic. A few things to notice before we can go ahead and do the mechanics is the standard error of B1, which we'll need, is the standard error of the whole regression line divided by root n-1 times the sample variance of all the x values. You can see that, so that's a formula we'll need to use. You can see that as n increases, the standard error in B1 decreases. So as n increases in the denominator here, the standard error decreases. Our test statistic is going to be our estimate B1 of the slope from our sample minus what we're assuming in our null hypothesis, which is going to be 0, that beta 1 is 0, divided by the standard error we've worked out. And that follows an n-2 t-test because we're estimating mu and sigma, so we've got n-2 degrees of freedom. So let's go ahead and do the test. So for this test, we're assuming that the population parameter, the slope is 0, so in other words, there is no slope, so percentage body fat does not change with different size waists. And for H1, we're doing the alternate, that it is not 0, there is in fact a slope. So the percentage body fat does change. So we'll set our significance level at 5% as normal. Let's work our test statistic. We got 1.7 as the slope of the sample regression line. We're assuming under H0 that the slope B0 is 0, beta 0, apologies, not B0, beta 0 is 0, and I've calculated using the formula the standard error of B1 as 0.0743, and we get a test statistic of 22.9. Now we've got n-2 degrees of freedom, so 248, so all we need to do, as before with a t-test, is draw the picture and finish off the test. So the probability of getting our test statistic or worse is a very small number, less than 5%. Remember, you enter TCDF 22.9 up to infinity. The 9999 represents infinity, and the degrees of freedom at the end. And don't forget to write where you're getting it from, tables or your TI calculator. So we're going to reject H0 as P is such a small value. In this instance, there is evidence to suggest that the percentage body fat is increasing as waist increases. There is a slope for the regression line. And that's it. Now let's have a look at some different computer outputs. Now, an excellent student of mine who's very curious was doing a past paper free response question and posted this on our discussion board to the class and said, what are all these numbers? Hopefully now they'll make sense. So when you're looking at a computer output, they all look different. Basically, you don't need to look at the R² adjusted here. That's for multiple regression. So that one is for multiple regression, which is not in AP, but if you do that in future, we'd use that. So this is the overall R² of the model, which is pretty low in this case. Look for an overall standard error. This could be called S or SE. There's different ways. That's the overall standard error, which we need to compare one regression model with another. It's a good indicator. Now, these are our coefficients, B0 and B1. So the constant would be B0, that's my y-intercept, and the semesters is B1. So from this we can generate our least squares regression line of our sample. It's going to be a y-intercept of 34.018 plus a slope of 1.1594 and times semesters, which I'll call x here. So that's how you get the least squares regression line from this table. Now, this is the standard error of our coefficients, and that's used to calculate the test statistic, which gives the p-value. So you can see here that if we look at the slope one, B1 under the null hypothesis is 0, and under the alternate hypothesis, sorry, B0 is 0. Sorry, B1 is 0, and B1 is not 0. Sorry, B1 is not 0. Then we can see that because this is less than 5%, we'd reject the null hypothesis, and actually we do have a slope here. So what we're saying here is that for one increase in a semester, that something would increase by 1.1594, the fitted y value. Also, you can see that, I don't know if it's interpolation or extrapolation, but we can see that also we do have a non-zero y-intercept as well, because we rejected the null hypothesis for that. So that's how to interpret all those numbers there. Let's have a look at a different computer. So I got this one from Bock et al., Modelling the World, the good AP stats book, and you can see it's laid out a little bit differently, but it's very similar. So you can see here that they've given the test statistic, standard error of the coefficients, the actual coefficients again. Here they've shown that coefficient is the y-intercept and that this coefficient is the waist, and that's the example we just did. And so hopefully you can see that everything is looking similar. And the overall standard error is here, 4.713. Let's have a look at another one. And here's our final one. Again, very similar. You can see all the different things. There's the coefficient B0. They've called it constant. That's very common. Waist here is here. And you can see, again, the tests, which are way less than 5%. So we've got a non-zero constant y-intercept and a non-zero slope for the population regression line. And they've shown the degrees of freedom, etc. So that's it. Thank you very much for watching. I'm going to make another video on how to make data more linear. So when we've got problems of that, for example, curves or fanning, heteroskedasticity, that we can fix those and then perform regression. So thank you very much. If you like this video, apologies it's a bit long, but a lot to explain. If you like this video, please hit on like and subscribe to my channel, and I hope everyone has a wonderful day.